Good morning to all and hope everybody is well. First, in behalf of the Global Seaweed Star Philippine team, let me thank the organizing committee for inviting me to grace this momentous event of an FRDI. It is such an honor. Today's presentation is about safeguarding the future of the seaweed aquaculture industry of the Philippines. The Global Seaweed Star is a 4-year challenge-led program from October 1, 2017 to December 31, 2021, funded by the Global Challenge Research Fund of UK Research and Innovation. This program brings together an international team of experts in science, policy, and economics from 9 partner institutions across the United Kingdom, Philippines, Malaysia, Tanzania, and Canada. To begin with, let's take a look at the global status of seaweed production based from FAO reports. This is a summary of production to include outside Asia. China is the biggest producing country with more than 20 million tons wet weight, with a market share of 56.75%. These are mainly temperate or cold water species like Porphyra, now Neopyropia, Saccharina, and Undaria. This is followed by Indonesia with almost 10 million tons, mostly Capophycus and Eucuma, and a little of Gracilaria. South Korea produces also the same species like China, and this country comes third. Our beloved Philippines ranks number 4 with 1.5 million both farm and from wild populations with a market share of 4.2%, while Malaysia produces 188,000 tons wet weight. Asia is the leading seaweed producer of the world as reflected in this table and graph. In terms of Capophycus and Eucuma cultivation, we rank number 2 to Indonesia. We should remember that Capophycus eucuma commercial cultivation was pioneered by the Philippines in the early 70s until we were overtaken by Indonesia sometime around 2008. It is highly understandable because Indonesia has 17,000 islands and the Philippines has only 7,000 plus islands. So you can just imagine the total areas being planted with seaweeds in Indonesia. Other countries in Southeast Asia and Africa contribute to a little extent. If we take a look on this graph from 1996 to 2020 seaweed production, it can be gleaned that an increasing pattern of volume was seen from 1996 to 2011, though in small quantity, but thereafter, since 2012, a decreasing pattern. In fact, it's a roller coaster. Information from the industry has reached me that 2021 will not be a rosy year for seaweed production due to the impact of COVID-19 pandemic. Seaweed carrageenan industry of the Philippines is worth 252 million US dollars according to FAO. Its volume of production as a marine commodity ranks number 1, but in terms of export value, it ranks number 3. Looking at the graph at the upper left corner, it is reflected that there is a decreasing pattern of production. Along this decreased production, there are 5 major phyconomic issues. 1. Repeated vegetative propagation of K. alberesi. Since 1970 to the present times, cuttings from harvest, selecting only the young and healthy branches, are taken as new seedlings for the next growing period, and this is repeatedly done. 2. Long-term production as a monocrop via extensive surface cultivation. Both practices led to low genetic variation and loss of strain vigor, further leading the biomass susceptibility to pathogens, diseases, and epiendophyte infestation as shown on the picture on the right. 3. Poor farming practices and management and lack of biosecurity measures. Despite available new technologies to be adopted from local research and innovations and from other countries, Traditional practices handed down from the first generation of seaweed farmers to their next kin still prevail to the present times, leading to low productivity and overall production. 4. Adverse effects of climate change, especially in coastal shallow waters. Therefore, a shift from shallow fixed-off bottom cultivation to deeper waters using hanging longlines, multiple rough longlines are encouraged in available areas with corresponding appropriate species and strains. And 5. The existence of several risks, especially at the production segment, by the seaweed farmers, which must be addressed to sustain the livelihood of tens of thousands of seaweed farmers. So the biggest question on how to address the declining production problem, as seen at the upper left corner slide, keeps on bugging the stakeholders. With all the published papers, personal experiences of yours truly, plus the works of colleagues in the academe, we can possibly solve the problem together in order to have a robust, sustainable, and successful seaweed aquaculture industry. I cannot do it alone. You cannot do it alone. It is a concerted effort of everybody from the different sectors of the value chain. There are four major possible strategies to address these problems. 1. Conservation of wild populations as sources of new stock. Based from the Global SeaweedSTAR research results, we have still available new stocks to choose from. Biobanking of these potential new wild populations is thus imperative for future sources of mother plants for domestications after a thorough research and ultimately for possible commercial cultivation. 2. Establishment of seedling banks through the use of tissue culture techniques and sporulation to generate new and improved seedlings. There are available technologies for both to be adopted. 3. Whatever produced in the lab through tissue culture and sporulation, the establishment of land-sea-based nurseries is necessary to generate and scale up year-round availability and accessibility of good quality seedlings. And 4. We must adopt good aquaculture practices for seaweeds from A to Z, that is from selection of cultivation site and species strains, farm management and biosecurity measures, harvesting, post-harvesting to marketing of the dried seaweed. In 2017 to the present, the Global SeaweedSTAR is working towards three key developments aimed in four work packages to secure food systems supported by sustainable aquaculture to provide the seaweed industry of the Philippines with practical solutions to the threat of yield-limiting seaweed diseases and pests. It is focused on identifying emergent seaweed diseases and pests and developing innovative new detection methods to provide an early warning of outbreaks as well as effective biosecurity practices and policy to prevent their spread. 2. Improve the resilience of commercial seaweed strains to empower the Philippines to develop and test new commercial seaweed strains for increased resistance to diseases and pests under fluctuating environmental conditions and climate change. The knowledge gained will be incorporated into farm management protocols to ensure maximum crop yield at farm sites. And number 3, support sustainable livelihoods and economic growth to improve understanding of the social, political, and institutional landscape of the seaweed industry of the country, with particular focus on biosecurity, gender equality, and risk management. We work closely with local communities and national government to develop a robust approach to policy development to promote sustainable economic growth of the seaweed industry. So, in order to fulfill all objectives, several field surveys were conducted in the country. In particular, the four major producing provinces, namely Palawan, Bohol, Zamboanga, and Tawi-Tawi, from 2018 to 2019. The field surveys were completed in December 2019, just in time before COVID-19 started. For package 1, ice disease showed low prevalence at all sites surveyed except in Davao, which had 100% incidence during the time of sampling. That no significant differences were observed between shallow and deep water seaweed farms as far as the prevalence of ice disease is concerned. That epiphytic filamentous algae, black spots, and grazing were observed, albeit at low percentage. However, the presence of macroepiphytes like sargassum and ulva was more evident in Luzon than in other places. Other macrophytes like Lingbia and Gracilaria were also observed. All the results obtained suggest the widespread occurrence of yield-limiting diseases and pests affecting eukymatoid farms in the country. Hence, strategies like diagnosis, surveillance, and management of these pests and diseases are to be considered seriously in order to ensure a sustainable expansion of the seaweed aquaculture industry of the country. For package 2, a knowledge, attitude, and practices survey was conducted to assess how seaweed farmers operate and manage their farming. Their knowledge was fair at 50 to 75%, attitude good at more than 75%, and practices fair at more than 75%. All this science-based information gathered are relevant in formulating recommendations to our policymakers to consider seriously to a much better seaweed industry of the country. For package 3, we were able to gather diversified color variants of farm and wild populations of eukymatoids. That external morphology and molecular analysis show that K. alversi is distinct from K. striatus, much more to Euchyma than Ticulatum. Based from our collections and molecular analysis, there are new haplotypes, especially from the wild populations, which are possible new species which can be studied further for future sources of new cultivars, for domestication, and consequently commercial cultivation. Further, this needs conservation of wild population through biobanking to preserve their germ plasm. And for package 4, focus group discussions were conducted among seaweed farmers, while one-on-one interviews was done among traders, exporters, and processors. The social structure and nature of support mechanism were explored during the FGDs. As a result, the first social network analysis was made at the farm level, that is from the production segment, to understand the differential access of women and men to information, resources, and services. A strong reliance on internal support source, that is the family, across the selected parameters like training, farm preparations, production, and gender differences on the extent of access to external sources were gathered. This study highlighted the relevance of using S&A in value chain analysis to understand the relationship patterns among the actors and their implications on policymaking and overall governance of the seaweed industry. Further, Package 4 looked into the risk management of the farmers, traders, and processors. There was the presence of environmental risks like disease and pest infestation as perceived among the seaweed farmers, and there were gender differences in awareness and knowledge of these risks, while the traders and processors risks like volatility and of supply and poor quality of raw-dried seaweed, increased competition between traders and processing companies, poor governance resulted in the adoption of informal and market-driven strategies to prevent or minimize losses, and lack of government support to engage in product development and diversification were identified. To highlight our efforts and accomplishments to this date, we have 6 publications in scientific peer-reviewed journals. If interested to have a copy, please email me or the senior authors. Likewise, a brochure in 4 different languages written in English, Filipino, Bisaya, and Tausug for the different stakeholders, academia, and interested parties are now available. So we have 5 major economic issues and 4 possible strategies to address these concerns. Probably you may ask this question: did Global Seaweed Star project address all the strategies? To be honest, no. But we have just started strategy 2 and later proceed to strategy 3. But we have fulfilled strategies 1 and 4. In order to supplement what we at Global Seaweed Star has done, and in answer to strategies 2 and 3, our previous works at CFDEC, AQD, my collaborations with NSDC, farmers and colleagues in the academe somehow have laid the foundation for these 2 and 3 strategies. Before we discuss further about strategies 2 and 3, let me share what Gashon 2017 reported that there are 3 ways how to control marine plant diseases in order to have robust seaweeds. These are: first, nutritional intervention, that is, making the host stronger; second, breeding disease-resistant algal varieties; and third, challenging and countering the pathogen with microorganisms friendly to the host. Personally, and with my collaborations with colleagues, we were able to address partly strategy 1, that is nutritional intervention using seaweed extract biostimulant. Let me first describe first let me, let me describe first what biostimulants are. There are many formulations of biostimulants with varying ingredients, which includes the following: humic substances like humic and fulvic acids, seaweed extracts, beneficial bacteria and beneficial fungi. Other products may contain chitosans, which is a soluble version of chitin, protein hydrolysates, and inorganic compounds like the silicon. To begin with, seaweed extract biostimulant, in all our seaweed studies, we use Ascophyllum nodosum, locally known as rockweed. These are abundantly distributed and found along the shorelines in cold areas of the northwest coast of Europe, northern Canada, and the United States. The seaweed extract is known as Ascophyllum marine plant extract powder, or simply AMPEP. Literature reported that AMPEP enhanced root vigor, increased leaf thallus chlorophyll content, increase in the number of leaves and branches, improve fruits and biomass yield, heighten flavonoid, that is the antioxidant content, enhance vegetative propagation, and more importantly, improve tolerance towards abiotic stresses like drought, freezing, high salinity, temperature, and light intensity. This seaweed extract biostimulant called AMPEP was tried in several species and strains of euchymatoids. First, it was done in micropropagation or tissue culture of Capophycus albersi as reported by Hurtado et al. 2009, followed by the reports of Bunke et al. 2011, Tibubus 2017, Ali et al. 2018, and 2020. These new plantlets generated from the blob were further mass-produced, then grown in tanks, and finally outplanted in floating cylindrical net cages. And this was tested further at NSTDC, a government seaweed research center in Sorsogon, for mass production and sea-based nursery in 2010-2011, and consequently for distribution to seaweed farmers in 2012, which were later tested in a commercial farm in Zamboanga City in collaboration with the Seaweed Farmers Association in 2011 to 2012. Robust and ice epi endophytes free K. albersi were harvested after 45 days. My collaboration with Dr. Ali in USM Sabah started in 2016 and later continued at USM Penang, his current affiliation. He did several studies of different strains of Capophycus using seaweed extract from mass propagation to sea-based nurseries as shown in this slide. We were able to generate several different color morphotypes and strains of K. alvarezii and striatus in his studies, which are now currently grown in Semporna Sabah in collaboration with some seaweed farmers. 2. AMPEP in sea-based nursery. Vegetative K. alvarezii tip in AMPEP prior to outplanting were grown in sea-based nurseries at 7 to 10 meters deep in cooperation with the seaweed farmers in Zamboanga City over a 12-month culture period. Good growth rates were recorded from October to May, that is from the onset of northeast monsoon in October to the latter part of the dry month of May. However, low growth rates were recorded during the southwest monsoon, that is during the rainy months of the country, from June to September, when temperature and salinity readings were lower from the optimal values. The use of AMPEP resulted to a higher growth rate of 6.6 to 7.5% per day after 21 days of culture at the sea-based nursery. Also, robust branches with abundant multilateral shoots were obtained, and ice and endophyte free with darkly pigmented seaweeds were harvested. 3. AMPEP in field cultivation. This was done in cooperation with seaweed farmers in Semporna, Sabah. These are K. alvarezii generated from micropropagation using tissue culture techniques. In order to facilitate and expedite the use of tissue culture of euchematoids for field cultivation, a guidebook is now available for use. Please email the authors if interested to have a copy. 4. AMPEP in the mitigation of endophytes. Likewise, pre-dipping of K. alvarezii, that is vegetatively grown, with AMPEP before outplanting significantly reduced the incidence of macroepiphytes and Neosyphonia and Falcifolia, two very harmful epiphytic filamentous algae, as reported by Borlongan et al. 2011, Ali et al. 2018, and 2020. K. alvarezii treated with AMPEP had much lower percentage of endophytes, less than 30% as seen in Figure A, while those untreated ones have more than 50% endophyte incidence as seen in Figure B. For mitigation of macroepiphytes, Hurtado et al. Claim that even though the seaweed is enveloped with thick green filamentous algae, once you remove the macroepiphytes, the thalli branches have clean, brittle, but smooth and shiny surfaces, and no traces of bruises brought by the covering of the macroepiphytes as shown in K. alvarezii and K. striatus. 5. Carrageenan quality for RC and SRC. The story of seaweed research is incomplete without doing Carrageenan quality analysis. The more complete study of Ali et al. 2018 and 2020 to include not only Carrageenan yield and gel strength but also viscosity revealed better qualities with AMPEP-treated Capophycus species than those untreated ones, though each species perform differently. There are more to be done to boost the immune system of the seaweed to combat its vulnerability to pathogens in order to maintain its vigor and robust growth. We have, we have to identify the modes of action and the metabolic pathways by which the complex AMPEP extract acts, especially when the cultivated seaweed exposed to increasing surface seawater temperature and salinity, fluctuations and photoinhibitory irradiance, and attacks by pathogenic and opportunistic organisms. All these studies will lead to improved stress tolerances in eukymatoids and consequently obtain higher productivity and enhanced quality characteristics. However, it is not only nodosum that fits all sizes, as they say for eukymatoids, but there are plenty yet to be explored, tested, and topped, especially our brown seaweed sargassum, which is abundant all over the Philippines. So let's join hands together and do more seaweed research studies for the good of the industry. The use of chemical fertilizer by few seaweed farmers brought more problems than solution, primarily to their trial and error practices. Educating them by showing or demonstrating the best aquaculture practices by competent authorities will surely enrich their knowledge and practices to improve their production, and ultimately their crops will be highly acceptable by the processors locally and globally. Earlier reports have provided proof of concept with very promising results on the use of seaweed extract for eukymatoids. This slide shows a comparative summary of the pluses and minuses on the use of seaweed extract phycobiostimulant versus chemical fertilizer to seaweed cultivation as to sources, cost, availability, efficacy in terms of growth, response to abiotic stresses, carrageenan quality, and impact to environment and humans. Apparently, the seaweed extract phycobiostimulant provides more advantages or pluses than the use of chemical fertilizer. Our accomplishments at CIVDEC AQD, the Global Seaweed Star project, and my personal collaborations with NSDDC and with seaweed farmers will contribute to the strengthening and safeguarding the future of the seaweed industry of the country. However, I would say that the pursuit for further R&D and R&I endeavors must continue to maintain a robust and sustainable industry with full and unwavering support from the government and private sectors. Thank you very much.